Okay, so before I even talk about KSP and the type of problems that we're going to be looking at today, I just want to do a quick review about Le Chatelier's principle and Q versus K. So we know when we have a chemical reaction that is an equilibrium system, it can go forward and backward. So I can have this reaction, and if it's an equilibrium system, it can go back and forth. So we can make the reaction go forward to make the products. Now we can also shift the equilibrium to go backwards and recreate the reactants. So when we're looking at that and we're trying to decide, okay, do we go to the product side or do we go to the reactant side, we compare Q and K. So we know that Q and K are pretty much the same thing. It's just K is going to be equal to the product versus reactant ratio at equilibrium. So if I have this particular reaction, K will be equal to this. If I am looking at Q, well, it's the same thing. It just could be at any given point of the reaction. It doesn't necessarily need to be at equilibrium. So when you have these two values and you have K and Q, well, you know, we're always trying to get back to that ratio. We're always trying to get back to the value of K. So what we do is we will look to see whether Q is greater or less than K. So if Q is greater than K, we shift to the reactant side and we recreate the reactants. If Q is less than K, well, that means we need to make more products to make that value larger. So it will shift to the product side and make more products. So when we're trying to decide if a reaction is going to happen, whether it goes in the forward reaction or the reverse reaction, we always compare Q to K if we have those values to do so. So let's look at a scenario that you might encounter if you have a KSP problem. So if we want to predict whether a precipitate will actually form, well, first thing you need to decide, okay, do you have a product that's insoluble? If you have a product that's insoluble, remember, most things can dissolve if you have enough water, if you change the conditions enough. So if we're trying to actually decide if a product will form, what we have to do is we have to compare Q to K. We need to know how much or what that value of Q is, and we can compare that to K to see whether we actually create that product. So let's look at the reaction that we've got here. I've got 150 milliliters of a 0.00395 molar solution of barium chloride, and I'm going to mix that with 550 milliliters of 0.00775 moles per liter of potassium sulfate. So I know that this is the whole reaction right here. I have barium chloride, and I'm going to mix that with potassium sulfate. Well, the two products that I could make, remember it's double replacement, you're just switching. So barium will bond with sulfate. Please make sure you look at your charges. And then potassium will bond with chlorine. Well, I know this is aqueous because it's got group 1, and I know this should be insoluble. It even tells me the KSP is very low. So I am interested to know whether barium sulfate, when those two ions actually meet, will they form the solid or will they just be pulled apart? So really, this is what I'm interested in. I'm interested in whether knowing barium sulfate, the solid will form, or it will just be pulled apart again into the solution. So essentially, do I have high enough concentrations versus my volume here to create this solid? So if you're trying to figure out if you will make a product, so if you're going to make a precipitate, it's a Q versus K problem. So what we were going to do, we're going to figure out, okay, how many moles per liter do we have of each of these ions? And then we're going to compare Q to K. So remember, Q, so if we're looking at KSP, that's going to be equal to the barium ion to the first times the sulfate ion to the first. Okay, and we know the value of that. We know that it's 1.1 times 10 to the negative 10th And I know that Q really is the same thing, it's just at any given point of the reaction. So I need to get the value of Q and then compare it to this 1.1 times 10 to the negative 10th. So I need to know what's my molarity of my barium and what's my molarity of my sulfate. It does give me a molarity, but I have two volumes here. And essentially when you put these two things together, you're changing the volume. The volumes are additive here, just like in a titration. So what you have to do is you're going to figure out how many moles this is, and then how many moles you have of this, of the sulfate, and then get the new molarity with the new additive volume of 700. So I know that I have 0.15 liters of this barium solution, and everything, if you look at barium chloride is a 1-to-1 ratio. There's 1 barium chloride for every 1 barium. If there were 2 or more, I'd have to worry about that. All right, and that's going to be moles per liter. So that is going to give me 0.0005925. Now I'm going to do the same thing with the sulfate. And again, I'm going to take my volume and I'm going to multiply it by the molarity. And again, it's 1 sulfate for every 1 potassium sulfate, so I don't need to worry about that. If it was more than 1, I'd have to double it or triple it, whatever that number is. So now I have 0.0042625. Okay, now remember, this is the number of moles. In order to plug numbers into this, it has to be a concentration. So now we're going to divide this by the new volume of 700. So now my molarity here is 0.000846. And this volume is going to be 0.0042625. Okay, so now I've got those values. Let's plug it into the Q expression and figure out what that value is. So the concentration of barium is 0.00846. Multiply that by 0.0042625. So Q will be equal to 5.1 times 10 to the negative 6. All right, so now that's my Q value. So now I need to figure out, okay, is that larger or less than K? So what will happen? So remember, I always draw this a little diagram out. So in this case, Q is equal to this, 5.1 times 10 to the negative 6, which is definitely larger than the 1.1 times 10 to the negative 10th. So Q is larger than K. It's going to shift to the reactant side, and we have our solid. So a precipitate forms.